Well, so again, for the benefit of you folks online, I apologize for starting late, and thanks for hanging in there with me today. So we're going to talk about depleted uranium today, which is the complement of the enriched uranium stuff that we were discussing last time. There's some reading. You can read it if you want to. Don't read it if you press for time. It's in the additional reading folder on La Lima. The second half of today's presentation is pulled from that. As part of a public presentation I was required to give when I did some work for the Army on depleted uranium here in Hawaii. I went around to various places and public meetings. So we're going to talk about depleted uranium, what it is, what it's used for, the environmental effects of its use, and there's a couple of really different categories of the way depleted uranium is used in military applications. Fortunately, the worst of the two applications hasn't occurred in Hawaii, at least as far as we know, and so it's not as big of an issue as it is in other places, but it is a big impact in other places. And we'll talk a little bit about that. And then next time, as I promised last time, we'll talk about some of these fission nuclides that were part of the global fallout and are still part of local fallout associated with nuclear power plants. And so strontium 90 and yttrium 90, how they're used and what the health impacts of them are. That'll be next. So I showed you part of this slide last time, and it's kind of a repeat of stuff we've talked about before. During the enrichment process, where we're making some uranium-235 out of natural uranium, or at least uranium-235 enriched material, we're separating out a much larger mass of material that is depleted uranium-235 and call that depleted uranium. There's all sorts of categories of depleted uranium depending on how enriched we're making our enriched uranium, right? If we're making bomb uranium that's really enriched in 235, we'll get a ton of 238. If we're talking about making fuel rods, where we're only enriching 235 a little bit, then we get less 238. If we're taking natural uranium, then we're going to have a different isotopic composition of the uranium isotopes in our depleted and our enriched material than if we take stuff that's been reprocessed, stuff that had previously been used in, for instance, fuel that has ingrown some uranium-236 by neutron irradiation. So we will have a different isotopic composition, and this helps us understand the source of the uranium. It's also useful to note that most depleted uranium that's used in pretty much any application, but especially military applications, is not pure uranium. It's an alloy, usually alloyed with a couple of other elements to make it have the right ballistic properties. So just some stuff about uranium, so we can think about the environmental impact, right? It's a naturally occurring metal. There are three primary isotopes naturally on Earth: 238, 234, and 235. 234 is produced by 238 by alpha particle decay. 235 is another isotope. We've talked about these before. They're all radioactive. It's dispersed at low abundances in rocks, especially here in Hawaii. The highest concentration we find of uranium in a rock is in coral. It's about 2 or 3 ppm, parts per million. And so, the average daily intake of uranium in food and drink is about 1 microgram per day. And that's a very average number. It could be different if you eat certain foods, but that's pretty much it in general. So, more overview, we don't find uranium as a metal anywhere on it. Even in ore deposits, we usually find it as an oxide, usually as a reduced oxide because it's less soluble in water, and many enrichment processes that increase uranium up to ore concentrations involve water and redox. So we find it as oxide, and if you put uranium metal, like man-made uranium metal or something, on the surface of the Earth, it's going to rust, which is just an oxidation process. Uranium metal rust is kind of yellowish or blackish or mauve, ochre, those kinds of tones. It's not, bright orange or like iron rust is. And these are just some pictures. This is a pristine depleted uranium round. This is a depleted uranium round right after being fired into sort of patina on it. And these are various pieces collected here in Hawaii, where you can see they've been sitting out in, on bombing ranges and in fields, and they oxidize more or less. And it's important to note that uranium solubility is pretty limited in natural waters. It's got some solubility when it's oxidized, and that's sort of a natural pH. And when we don't have very much oxygen, so like we go down into a soil column and we're redox limited, we'll go down in sediments, it becomes really insoluble. Well, look at the PE-pH diagram. At a certain point, we go from uranium +6 to uranium +4, and the +4 is non-soluble. Something that really enhances the solubility is carbonate ion. So uranium makes a carbonate complex, and this is what, for instance, makes it have a really long residence time in seawater. There's a lot of carbonate. So if you add a lot of carbon to water, or if you add a lot of phosphate to water, you can make uranium more soluble. So if you think about a farm field that's contaminated with a little bit of uranium, if you're amending it with phosphorus, it's a possibility that you're helping to mobilize the uranium. Another thing about uranium that's interesting, which is really relevant here in Hawaii, is that uranium sticks onto surfaces, especially surfaces that are rich in iron. So we have iron-rich soils. This tends to immobilize uranium. It doesn't migrate through flowing water. It sticks onto iron. It also sticks onto organic matter. So this is the PE-pH diagram, right? The two water stability lines and pH across here. More soluble at basic pH in either oxidation state, but you know, the oceans, for instance, is one. This is obviously pH 8 or so, but here in Hawaii, our groundwaters and our river waters are nowhere up here at these kinds of pHs. We're usually acidic, and so you can see the separation between the soluble form and the insoluble form, and this has got uranium in the presence of carbonate, right? So at high pH, we make these carbonate complexes. At low pH, we don't really make the carbonate complexes. And you can see there's a switch from being positively charged to negatively charged, which is going to affect how it binds on the soil particles. And it's only when we get into reducing conditions, and this boundary is roughly the same place as the iron 3 to iron 2 transition in the center. Obviously at low pH, that's sitting way up here, but it behaves similarly, I would say, to iron at moderate pH. So this is a diagram that shows you, again, as a function of pH, the amount of dissolved uranium in different forms in a natural water that's got kind of all of the typical anions. And so what you will see is that around pH 6, plus or minus a unit or so, we make this phosphate complex. That's the thing I mentioned in like amended farm fields, where it's you know, the dominant species. We get up above pH, we make carbonate, and when we get down below pH 4, we have all sorts of odd things in addition to the oxide. We can make a little bit of fluoride, a little bit of sulfate, or whatever. But importantly, in the presence of iron, right? And so this is pH again, and the amount of uranium in the +6 form, the soluble form, that sticks onto iron, and so therefore becomes insoluble as a function of different concentrations of iron. 6 micromolar, 60 micromolar, 600 micromolar. And what we see is that at 6 micromolar, it's almost all bound at about pH 6.5, 7, something like that. And as we increase the concentration of iron in the particulate form, then more and more of it becomes bound at wider ranges of pH. So if we have a lot of iron around, uranium is immobilized. Okay, so now let's talk a little bit about depleted uranium. So depleted uranium can be made from natural uranium. And that's how a lot of the early stockpile of depleted uranium in this country was made, right? We had an earlier nuclear weapons program, an earlier nuclear power program. There was a lot of uranium-235 enrichment and big piles of 238 sort of piling up, and the depleted uranium stuff. So that tends to, uranium-238 enriched, or what we call depleted uranium, tends to have lesser amounts of uranium-235 and the daughter uranium-234. That uranium-234 has got like a 234,000 year half-life. So once we pull it out, it's not going to grow back in very quickly. It takes some time. So DU has a lot more of the long-lived isotope, the 4.5 billion year half-life stuff, and a lot less of the short half-life, 700 million and 240 or so thousand year half-life stuff. So it has several civilian and military uses. We're going to focus on the military uses because that's how it was used here. And we'll talk a little bit more about some of what those are in a moment. But when it's used in weapons, is alloyed with other metals. And again, we'll look at a little bit of that stuff. And that alloy behavior affects things like how does it behave while it's being fired? How does it behave when it's impacting on something? It turns out, even though it wasn't planned or people care about it, it also affects how the metal object that is left behind from a projectile behaves in the environment. Does it rust? Does it break apart? Et cetera, et cetera. And so, we can introduce extra uranium into the environment in really high concentrations in a form that we don't find it in nature, the uranium metal, when in some cases it's on purpose. In the military uses, it's on purpose. In civilian uses, it may not necessarily be on purpose, but we have accidents and that happens. And so, we can talk in general about what happens when we introduce a large amount of metallic substance into the environment. This is, for instance, an example of a typical alloy of depleted uranium that'll have, some uranium, a little bit of molybdenum, a little bit of titanium, a little bit of niobium added into it, and these are different alloys. One is just pure uranium, one is uranium, a little molybdenum, etc. And this is the amount that it will, the amount of that chemical composition will affect the rate of erosion in the environment. And so you can see a pure uranium projectile or material or whatever is going to rust a lot more quickly than one that's alloyed with, for instance, niobium. And so what we're talking about here is really a process of oxidizing zero-valent uranium, uranium-0, like iron metal, to uranium-4, which is insoluble in pretty much all conditions, and then oxidizing that to uranium-6. And this is the stuff that can be soluble if we have carbonate or phosphate around, is insoluble if we have iron around or organic matter. And so it's got fairly complicated chemistry. Not only does this affect the fate and transport of uranium contamination in the environment, but it also affects the uptake into the ecosystem. Okay, so depleted uranium is a super dense metal, and it's used in a lot of applications. And there's three ways that we find depleted uranium getting into the environment. In probably until the 1980s, which is when the US started using it significantly in weapons, this was the primary mechanism of uranium getting into the environment was in processing plants. Think about the example I gave you around the Great Lakes last time, where part of the nuclear fuel cycle involves making rods and milling material into rods, and in military applications we're processing rods. And like all chemical factory plants, there's a certain amount of spillage that happens. And we'll look at one example of a place in upstate New York, which is kind of notorious for how much uranium they spit out into the landscape, and we can see where the uranium is currently found in soils and so forth. But this usually involves aerosols, like really finely divided particles, or water-dissolved effluents. And this, like I say, is a pretty big source of uranium to the environment, but it's really restricted to the places that do that. There aren't that many places in our country or even around the world that do this kind of processing because it requires really specialized skills and equipment. So then another form of depleted uranium that goes into the environment is in commercial, industrial, or military vehicles. So for instance, the biggest commercial application was certain early Boeing planes had a big tail fin weight of depleted uranium. It's a really dense metal, so you can get a lot of weight with a relatively small piece of material. And this was stuck in the back of the planes to help them have the right attitude when they take off and land. They don't do it anymore. I don't know exactly when it was phased out, but it's the older models. I think 707, 727 definitely had it. I'm not sure if 747's ever had it. We also find it in industrial vehicles and in military vehicles, not for its radioactivity characteristics, but for the fact that it's a dense metal, it's easy to work metallurgically, and it shields radioactivity. So Stryker vehicles, for instance, Abrams tanks, they have depleted uranium shielding, which shields the people inside from some amount of gamma radiation. You can use lead. That's obviously a really good metal for shielding, as we've talked about before, but lead's a very soft metal. It deforms really easily, and Du is almost as good. And so this is used to help protect people from external radiation. And then the new thing, and the thing that we'll talk about a lot, and the thing that a lot of people around the world are concerned about, if you Google this, are something that are called kinetic energy weapons or kinetic energy penetrators, which are basically depleted uranium munitions that when they are fired, they burn in the air, they oxidize, and they self-sharpen And so they are extremely effective at penetrating through very thick concrete, metal, etc. Whenever you hear them talking about bunker buster bombs, these are also usually at least have a depleted uranium tip. It's basically a material that has really excellent characteristics for weapons of war. The problem is that when we use them, or when militaries use them, these aerosols are very, very fine particulate material of uranium that gets released into the environment. And once it's released, it's very hard to get back out. The soldiers who are in the area where it's being used breathe this stuff in, which is obviously not good, because then we get an internal source of alpha particle radiation, which, as we've talked about already, is the worst way to be exposed to alpha particles. It gets into, civilians obviously are affected. One of the places that the U.S. used it a lot was in the Bosnian War, and there are farm fields that are now full of this stuff that it's basically really hard to remediate. It can be remediated, but it's extremely expensive. And so, and the U.S. isn't the only country that uses this stuff or has used this stuff, but we were the first to kind of introduce it to the world. And in fact, when we introduced it, we gave it to the Israelis first. And for their 7-day war in the early 70s, it was like, hey, we got this really cool stuff. You want to check it out? And they used it, and they're like, yeah, we like it. The U.S. hasn't admitted to using it until later conflicts in the 80s, but in any event, it's, the cat was out of the bag. We currently have a lot of limitations on using them. The military has a huge arsenal of depleted uranium stuff, but they understand that it has been implicated in a lot of impacts on our own troops. And so it's sort of kind of like in reserve for like if we really need it, sort of like atomic weapons in a way. It is by no means as bad as an atomic weapon. I just want to make sure that you understand that. And so, we have to superimpose the uranium introduced into the environment from any one of these things with the kind of natural uranium in a place. If you're in a place that has a lot of uranium, then the ecosystem and the foods that come off the ecosystem that support humans are already going to naturally have higher uranium than in places with low uranium in the environment. Like Hawaii is a place with low uranium in the environment. And so, as I mentioned before, with other kinds of contamination, once you already have a high natural concentration of something that is potentially not good for you when you ingest it, it means it's more sensitive to introduction of more, right? Because you're closer to the threshold where it becomes a problem. So this is a little bit more pictures about depleted uranium. This is a DU round, a kinetic energy penetrator going through armor and metallic armor on, like, for instance, a striker vehicle or a tank. This is what a tungsten round would look like. Tungsten is a really common metal for a lot of high caliber, military weaponry. And you can see that whereas this thing deforms and doesn't go all the way through, the depleted uranium goes through and it almost looks as good on the way out. And here's just a couple examples of, a weapon made out projectile of DU and tungsten. Obviously, there's a lot of lead that's used as well. Lead's even worse than this, and it volatilizes a lot. And so, whereas lead is still very common in small caliber bullets, in military applications, it's not so common. There's a place, the Nevada test site and training range. This is the place where we did all of our below ground testing in once the nuclear test ban treaty came in '64, that we were still actively testing there in the 80s when I did a little bit of time as a grad student in Lawrence Livermore National Lab, which is a Department of Energy facility that was measuring soil composition of post-test soils to kind of look at yields and stuff. And part of this huge reservation is a place where they just like test other weapons. And so this is like, they like put tanks out there and they like fire stuff at it. And I'm sure it's fun for the people who do it, but this is just an example of what they call a heavily used target, something that has had a lot of depleted uranium fired at it. And as I say, these modern depleted uranium munitions, yes, they're really good at being munitions, but the thing is that part of what makes them so good is this so-called self-sharpening characteristic. The self-sharpening characteristic comes from the fact that they burn in the atmosphere. And as they're burning, they're releasing more uranium-rich particles as an aerosol into the environment. And so certain ones of these, they're not all the same, but certain ones of these produce really large amount of particles. You can also imagine that as they impact, they're going to make even more aerosols. And so in fact, vehicles that have been exposed to depleted uranium on the battlefield have to be considered as radioactive waste. There's that much uranium in it. This is a couple more examples of what it looks like when a depleted uranium round goes through a very thick piece of metal. You can see the kind of hole it makes. There, as I say, I mean, that's obviously a very large caliber projectile, but they're really effective. And, militaries like stuff that's effective. So a little bit about the toxicology. When we're talking about radioactive materials with kind of long half-lives that also exist in nature, and uranium's a good category of that, we have to think about toxicology from two perspectives. One of them is from the radioactivity, and one of them is from the chemical toxicity of just the uranium. And it turns out that in most situations where you or I would become exposed to uranium, this is a bigger issue than this, because there's not high radioactivity material. However, if you get a really large quantity of uranium ingested into your body, either through one of the traditional pathways, or we have to consider a fourth pathway for for military applications, what we call intramuscular, like if you got shot with or hit with shrapnel or something like that, you can cause significant damage because you're having alpha particle emitters internal to your body. Now, uranium is really pretty soluble when it's oxidized, and so it can be flushed out of the body relatively quickly, although it does bind up with organic matter and certain proteins in the body. So the kind of two main target organs for uranium toxicity, these aren't the only ones, but the main ones we find in, for instance, like workers in uranium processing plants and so forth, are sort of the kidneys and respiratory disease. And we'll talk about both of those things in a second. The respiratory disease might be a kind of case of mistaken identity, in the sense that the uranium people are exposed to is uranium hexafluoride, which is the gas form that goes into the centrifuges. If people breathe it in, they can have, they get respiratory disease, lung cancer, etc. But it's probably related to the fluoride, the hydrolysis of the uranium hexafluoride to the hydrofluoric acid in the lungs, as opposed to the uranium itself. But when we ingest it, we get large quantities of uranium in the body. The kidneys are the main organ that are trying to filter it out, and you do find cases of toxicity there. So the two main pathways, we talked about this before when we talked about toxicology. We have ingestion and inhalation. We also have dermal contact. With alpha emitters, something on your skin is really not that big of a deal, right? It's because it isn't that, these materials are not that radioactive, and because they're emitting alpha particles, which don't even go through a piece of paper, your skin will protect you. But as I say, there's this other pathway we have to think about, which is intramuscular, which is pretty much only restricted to military applications. So this is an example of a literature review of various papers as a meta-analysis, and we're looking at a whole bunch of different causes of death from, they heard a whole list of different kinds of cancers, and then here's some sort of, urinary tract, including the kidneys, kind of diseases. And what we have in these kind of diagrams, I think we've talked about them before, but this line 1 is the risk of getting one of these things in the general population. And then the bar is basically the study. And we'll have the actual cases, and then we'll have some uncertainty. And the smaller these little bars are, there's fewer cases, right? There's like only 30 cases here, where up here we've got 3,300 or 30,000. So it's got a blockier box. The important thing to note is that most of these boxes, for most of these exposures that have been documented, have a less than one occurrence, meaning that the frequency of occurrence of these kinds of cancers in a population exposed to uranium is equal to or less than, except in a couple of cases where these error bars jump across, the general population. That doesn't mean that these things can't cause these problems, but there isn't a statistical correlation that suggests that there's a very obvious higher incidence of any of these kinds of cancer in people exposed to uranium from the general population. Now, if we look in a little bit more detail at the two main types that I was mentioning, kidney failure from ingestion and respiratory disease from breathing it in, these are individual studies now. And you can see, some of them have a lot of participants, some of them don't have many participants. So if we look up here first at kidney failure, We see a similar pattern to what we saw on the last slide, but more variability. There are some studies, just a few patients, 6 patients, et cetera, that show a really very significant increase in the probability of getting kidney disease if you're exposed to uranium. And then there are some things that straddle the line and some things that don't straddle the line, right? And this is kind of the nature of the beast with these kind of studies. In a meta-analysis, these things would all be condensed down and averaged into one thing. But there are probably conditional differences between each one of these studies, that there are some conditions where it does result in kidney diseases and some conditions where it doesn't. It's not a huge, positive correlation, but there's a significant probability that people exposed to uranium at high concentrations that ingest it will experience kidney failure. Now, this one here is respiratory disease. Again, there's a whole bunch of studies, and the average of these studies is less than the average of the average population, but there are several studies here, including the very biggest one with 1,568 participants, where the probability is higher. And there's a couple over here where the probability is a lot higher. And so, this is increased mortality beyond what's seen in the general population. And I think it is well accepted that high concentrations of uranium in the vapor phase are toxic to the lungs. The question becomes, is the form of uranium that is produced as an aerosol when it's being used in a kinetic energy penetrator and being released into the environment, the kind of uranium that does this? Or is it the uranium hexafluoride form that workers in uranium processing plants, which pretty much all these studies have been based on, and it's only that and the fluoride component of that, and so that the aerosols from depleted uranium aren't as bad. We just don't know. We don't have the retrospective studies yet. This stuff's starting to happen from soldiers that were exposed to uranium aerosols in high concentrations in the late 80s from the first Gulf War, but it's inconclusive, at least as far as I've seen. And I haven't looked at the literature in the last couple of years about this, but the question is out. But we do know that uranium aerosols in some forms can be toxic. So when you think about these exposure risks, right, you have to think about, and this is true for any metal or any contaminants in any setting, you have to have use cases, meaning how does a person interact with things? If you have a contaminated space and someone's in it all day, they have a different level of exposure than someone that walks in and out of a room quickly, right? And we have contamination in an environment. We might find different levels of contamination, especially if we have contaminated soil. Kids like to play and dig in the soil. They have a higher amount of exposure than someone who's just sort of walking back and forth from their car across a field and not digging it. So this is the radiological estimate of the amount of dose that one might get for 3 different levels of contamination in the presence of a military application of a depleted uranium kinetic energy penetrator. So we've got level 1 inhalation of impact aerosol, inhalation of resuspension aerosol. That would mean impact aerosols, like you're there right when it happened. Resuspension is, the particles settle out and then people are driving through or whatever, and dust gets kicked up again. So it's going to be less. So you can see that someone has made the estimate. These are just estimates that 250 milligrams, 10 milligrams, that can be converted into doses and sieverts, right? And you can see this is a pretty high dose. These are millisieverts, obviously. So that's 0.022 sieverts. Still an acceptable risk from radiological perspective. There's level 2 ingestion if you're sitting inside a contaminated vehicle, a level 3 inhalation of resuspension aerosol within a contaminated vehicle. That each one of these things kind of goes down. And one thing you'll see here is inhalation of plumes from fires. So if we disperse a bunch of uranium into the environment and there's also fire, like a brush fire or a forest fire or grass fire, it will resuspend some of this uranium along with the ash. But the estimate is that it's a lot less. And they've in fact done tests. We've done tests here, at firing ranges in Hawaii, where air filtering monitors are put up during controlled burns, which they do periodically around their firing ranges to control vegetation. And they filter it for various things, and they look at the amount of uranium, and it's pretty low. Doesn't mean it can't be high, but it's pretty low. So then this information is with this kind of amount of, you know, average amount of intake and a worst case scenario intake, you can, and taking all that literature data that I showed you on the last couple slides, you could make some guesstimates. And they're rough estimates, but on the number of excess deaths you might get in a group of 10,000 soldiers, not acutely, but because of the chronic exposure. Because what happens with radiological contamination of this type is that it gets into your body and it's cumulative. You're producing uranium nuclides over your lifetime, you're absorbing alpha particles, and you have this sort of progressive decay. And so, you know, they're estimating that, you know, the worst case possible scenario out of 10,500, 585 will die of lung cancer, and 42 will die of leukemia, and the kidney failure is not included on this list. But if we look at the sort of, you know, level 1, level 2, level 3 exposure using examples from this list, those risks are a lot less, right? And so this acknowledges, I mean, military understands that there are risks, and you know, war is a dangerous thing. There's lots of other risks as well, but they decide what is acceptable and what's not when they decide what their practices are. So this is a little bit more information about uranium in kidneys, and how uranium behaves in a person's body depends a lot on how it was introduced to the person and in what form it was introduced. So is it an aerosol? Is it you know, little particles? Is it pieces of metal? Is it already dissolved? And if it's dissolved, what form is it? If it's solid material, like maybe, you know, you were digging in the soil and you got a little bit of particles in your mouth, but it's already oxidized, like is it oxidized to the yellow cake form or a higher amount of oxidation? And you can see here, there aren't very many people that were studied. The number of participants is relatively small, but a positive effect is shown with a plus, no effect is shown with a minus. It's sort of semi-quantitative, like 3 pluses is more effect than 2 pluses. You have to kind of read into the paper to see the details. But you can see that if you ingest uranium, you know, in drinking water, you can definitely have an impact on your kidney. If you inhale oxidized uranium particulates, it gets into your fluids in your lungs, it dissolves, and then it gets into your blood flow and is eventually filtered out by the kidneys. Again, you can have an effect. If you have an intramuscular uranium metal exposure, meaning you got hit by a bullet or shrapnel, you probably don't have an exposure, at least in this very small study, or an exposure rate. These are other types of exposures to different forms. So uranium in the acetate form, the nitrate form, inhalation of the fluoride form, you know, et cetera, et cetera. And you'll see here that some of these have really pretty decent effects. Maybe a couple of them don't, or they have relatively small effects. But so it does depend a lot on the particulars of exposure. So this is some looking at sort of what happens when someone is exposed to uranium, and how the concentrations build up in the body, how they reduce back out by the sort of normal flushing processes that happen. And it depends again on what you're exposed to, how much you were exposed to, what chemical form it was in. But for instance, this is sort of studies in kidneys from natural and acute uranium exposure. So natural exposure is something like we all get every day. Every time you eat various foods, you're getting a little bit of uranium. It's small, but it's there. And acute exposure is obviously something that happens right away. And you can see that this is sort of the impact on the kidneys, the amount of uranium that's sort of building up in them. And after exposure time, this is time in months, so, you know, whatever 1,000 months is, 12 months in a year. I'm not going to try to do that math, but the uranium slowly builds up, right? It's being filtered out and not washed, filtered from the blood, not washed from the kidney. If you ingest it, if you eat it, it's got a much shorter half-life in the body, right? So this is time after intake in days. This is after 1 day, it sort of builds up and then it starts to flush out again. So a lot of it does depend on the pathway of exposure. This is what happens after level 1 inhalation, where you're getting it into your lungs. And you can see sort of, again, they always have like a central estimate, which means sort of the average and the worst case scenario. And so you can see these different concentrations. And in details, this is the chemical toxicity and the radiation dose. They're slightly different, but the concentrations still take a long time to go back down in terms of the toxicity that they're creating. And it's true whether we're talking about level 1 or level 2. The patterns of these things are the same. Just look at the scale. This is 100. and this is 1,000. So if you get that, remember level 1 was the worst case kind of type of inhalation, and level 2 was a little bit less bad. So the point being, it stays with you for a while. So now let's think about what happens when uranium gets introduced into the environment. So this is a diagram. You've kind of seen this before when we talked about what happens in ecosystems and soil columns. I just put a couple things together to sort of talk about the normal cycling we have of metals in the environment, how they interact with vegetation and land plants, and how we have dry deposition and precipitation events, soil forming processes, rock weathering, the formation of structural units, the change in pH as we go down, the changes in organic matter content. And remember, uranium likes to bind onto iron, and it likes to bind onto organic matter, especially at pHs less than 8, which are things that we find in the topsoil and in the B zone of soils, especially in iron-rich soils that are formed from iron-rich rocks like we have in Hawaii. So a lot of the net effect is that a lot of uranium that comes through the environment, whether it's natural uranium or contaminated uranium, ends up being bound up in the soil column. Now, there's also introduction of organic matter that can be natural or that can be artificial, right? We have a lot of agricultural fields here. Most of central Oahu, which ring the Schofield Barracks, which is where a lot of the uranium was used here, it's agricultural. And so when you enhance the soils, if you're just adding organic matter, manure, or whatever, you're lowering the pH, you're increasing the uranium content, you're probably immobilizing uranium. But if you're putting a lot of phosphate in the soils, amending the soils to help grow certain crops, then you could be increasing the uranium mobility. And we have to look at these things in the aggregate. But then we have over here kind of what happens when we introduce a metal object into the field, a projectile, right? It gets used. So to some extent, it gets disaggregated. We still find metal fragments. You can walk, I don't get to walk around, but when people walk around on the firing range, and they're all trained because there's a lot of unexploded ordnance out there, but they'll bring back pieces of metal that are as big as your hand, and little fragments and things that you can't see with the naked eye. And these things have various fates. I have another slide that talks about the fate more, but the basic fate in the environment is over some period of time, these objects are going to oxidize, they're going to disaggregate. Some of them are going to dissolve, some of them are going to be as particulates, they're going to work their way down into the soil column, especially in a firing range where they've been firing stuff there for 40 years. Things keep working themselves down into the soil column and redistributing up into the atmosphere and everything else. So it's a much more active environment than if you found these metal objects on a battlefield that was used once and then people walk away from it. And so you can imagine that the fate of this material depends a lot, again, on the environment, but ultimately some of this stuff is going to dissolve into water and then get worked up into this whole cycle. And in Hawaii, the short answer is that most of the uranium binds to soil. Now, I don't want to spend a huge amount of time talking about environmental impacts, but I just want to mention a couple studies. One of them, this is a recent study that looks at the sort of fungal impacts within soils that have been contaminated by uranium of soils with sort of 3 different conditions. Ones where there are no pine trees, but the fungi are present. Ones where there are pines that have these metacorrhizal interactions, which, if you recall, happen on the roots and affect the transfer of phosphorus between soil, and soil water and roots. And then cases where we have pine trees that are not myocorrhizal. Now, these are the names of the fungi that they looked at. These were actually, I wouldn't call them laboratory experiments, but they were artificial experiments in the fields where basically these existing populations were present, and they introduced some uranium, and they kind of looked at what happened over time. And in this case, they weren't able to identify what the fungus was, but this is the concentration of uranium in the fungi. And if you think about it, think about a food web when we're transferring material from sort of inorganic solid form into organic form, incorporating the organisms, and then it can be passed up through the food web. So this depends on how the uranium was introduced and what concentrations it was found in the digests of these separated fungi. But you can see that there's a lot of it is in a nitrate form, less of it is extractable with acetic acid. Acetate anion likes to bind uranium, and even less of it in uranium. But that the highest concentrations here that are in the fungi are in these fungi associated with these pines. In this case here, there's less. In this case here, there's more. I'm saying it backwards. Not having the fungi means that there's more left in the soil, and having the fungi means that there's less in the soil. And so people have not studied in great detail the impacts, long-term impacts of depleted uranium or any uranium use in the environment on the ecosystem. Like once people go away, what happens? Can you farm in those fields 10 years, 20 years later? But it's clear that it does work itself into organisms. And this is just another study. This is the concentration of uranium. And if you imagine there's natural uranium in the environment and there's depleted uranium in the environment in a place that's been contaminated, and the way we distinguish them is on their isotopic composition, the ratio of uranium-235 to 238. Turns out that natural uranium has a ratio of 235 to 238 by atoms of 0.00725. Right? You don't have to remember that number. And oftentimes, a lot of these diagrams will plot this in the reverse with 238 over 235 ratio, in which case is 137.88. But depleted uranium, uranium that has gone through this process of pulling out uranium that was used for enriched uranium, will have a much lower ratio here. Okay, and so the depleted uranium that was used in this environment, the end member composition is shown by this place called RGH. It's got a lower ratio. And just out of interest, if you looked at enriched uranium, stuff that was higher, like nuclear weapons, quality stuff, or nuclear fuel, it would have a much higher ratio. So now this is looking at earthworms that were living in these fields that had been exposed to depleted uranium and waters within the soils that the earthworms were obviously living in. And we can see in both cases that as we go farther and farther away from the source of the depleted uranium, the isotopic composition of the uranium, this doesn't tell us the concentration, but it's telling us the isotopic composition falls on a mixing line where we have more natural uranium the farther we get from the source and more depleted uranium in the earthworms as well as in the soil waters. And it turns out that in a lot of cases, this gives us a good way of kind of integrating the impacts of contamination, not just for uranium, you can use it for other metals as well, because the way earthworms work is they bring in soil particles, they adjust what they can from it, and then they poop out the rest out the back, and they tend to bioaccumulate metals from the environment. And so where you don't get a super precise concentration, or understanding of where the contamination is or isn't, but it gives us a gross idea of environments that are contaminated. And you can see that, even 50, 100 meters, 150 meters away from the contamination, that's pretty far. That's like 500 feet. You can see contamination in the organisms, right? So that is natural uranium, that's depleted uranium. Okay, so how do we distinguish uranium in the environment that's depleted or enriched? And again, it depends on the source. And so I like to think about this as isotopic fingerprinting, kind of like I mentioned last time with the stuff that comes out of the atmosphere from fallout. With uranium, because the numbers of atoms present, because it's a decay chain for some of the isotopes, is inversely proportional to the half-life, it's easier, instead of looking at the number of atoms, to look at the activity, the amount of radioactivity that's coming out. Because in a decay chain of secular equilibrium, for instance, uranium-234 or 238 in natural uranium are decaying at the same rate, even though the numbers of atoms present are different. So this is shown for activities for depleted uranium, right? So we got a lot of 238, we got a little bit of 235, we got more 234 in activity space, not in numbers of atoms. In numbers of atoms, there'd be a lot more of these. This is what natural uranium looks like. So these two guys are decaying at the same rate because they're in secular equilibrium. When we deplete, we pull out some 235. So this pancake is a little bit smaller than that one, and this pancake is smaller than this one, or whatever that is. And when we enrich uranium, like we do when we're making nuclear fuel or whatever, in a relative sense, we have a lot less 238, a lot more 234, and a little more 235. It's hard to show the difference between 0.07% and 0.7% and 5%, but that's basically what these two things are. Now, this diagram tries to show you a combination of what's shown here, these isotopic pools, and this is a generalization. You can deplete your uranium to different degrees, you can enrich your uranium to different degrees, but it gives us a family of compositions that I think you can see right off the bat natural uranium has equal amounts of these two things. And that's something we can tell really easily with a whole bunch of different methods. Depleted uranium has a lot more of this than the other isotopes, and enriched uranium has a lot more of this than the other isotopes. That's a simple way of thinking about it. But then we can also look at the amount of uranium contamination in the environment overall by looking at the net amount of uranium. We use the 238 as the most abundant isotope, it's the easiest one to measure. So as the concentration of uranium goes up in the environment, more and more contamination, we are going to get different isotope ratios as we mix that contamination in with natural uranium in the environment. Natural uranium in the environment is going to have this isotopic composition. If we just got like a little bit of contamination, then we would expect to find the uranium isotopic composition to be just a little bit different than this. And if we put in depleted uranium, it's going to be different in the direction of the orange ones. And if it's enriched uranium, it's going to be different in this thing. And as the concentration of contaminant goes up, we go farther from this composition to either this composition or this composition. So that's what's tried to depict here. These are relative ratios of what is observed for, this is the uranium-234-238 ratio, right, compared to the natural ratio. And so it's a ratio of ratios, and this is 235, right? And so in one case, I'm comparing this ratio, and in another case, I'm comparing this ratio. And as the uranium concentration goes up, depending on if we're contaminated with depleted uranium, natural uranium, or enriched uranium, we follow very different enrichment trajectories. And so when we go into a contaminated environment, we're going to take a whole bunch of samples and we're going to plot them up, and oftentimes it's relatively messy. But what you will see is that if it's depleted uranium concentration, as the uranium concentration goes up, the relative amount of the things that it's depleted in go down. The 234 and 235 go down. So we sort of sit at this lower quadrant of the diagram. And if it's contaminated with enriched uranium, then like for instance, you would find in soils around Chernobyl, then obviously you're going to go up along these trajectories. The more uranium you have, the higher the contamination. There are also natural sources of uranium. So for instance, in the processing of natural phosphate deposits from the environment where they're used to make fertilizers, one of the biggest plants in the world is in Syria, that there's a lot of rare earth elements and a lot of uranium naturally associated in those processes. And sometimes it's processed out of the phosphate fertilizer, sometimes it's not, but you can find highly contaminated environments. It's natural uranium. They have high concentration, but they always still have this natural isotopic composition. Just as sort of an aside. Okay, so this is some using application of this fingerprinting. So this is the inverse of the ratio that I plotted before, which is 235, 238. This is at 238, 235. So as I mentioned, natural is 138. So anything that has a ratio that's higher than natural, when it's plotted like this, it has less 235 than normal, which makes it depleted uranium. And anything that's got a lower ratio would have enriched in 235, would be enriched uranium. Okay, so this is in a plant. I'm going to show you a lot of data about this processing plant, but this is a place where they processed a lot of materials for both military and civilian uses in upstate New York. And we're particularly careful about effluents going into the environment. As you'll see in a second, this is a plant that's right in the middle of the town, and so people are being exposed. But this is concentrations and isotopic compositions, as you say, of uranium in water, in residence, and some standards. Whenever we make measurements, we measure a bunch of standards on our instruments so that we can make sure we're getting the right number. And so what you will see is, yeah, some people clearly had depleted uranium, a lot, a couple of people just a little bit above the line, but most of the people on the line. And this is, studies, where companies are trying to say, oh, look, all this contamination in the environment is not showing up in the water very much, but there are clearly some number of people in that small study that were showing the exposure. This is workers at that same plant, a little bit more information. So this is that same ratio that we had on the last slide, but now shown in reverse. So in this case, natural is 0.007, and anything that's lower is depleted, and anything that's higher is enriched. This is another kind of uranium, uranium-236. We don't find uranium-236 in natural uranium. Right? It was present on Earth when it formed, but it's got a shorter half-life and it decays away. However, in uranium that had been used in fuel rods that were reprocessed and purified, we do have uranium-236 because it's in a radiation nuclide. We find some uranium-236. So depending on what our depleted uranium was made from, and that isotope wasn't on that plot I had with the pancakes, but if you add this into the mix, it is increased in concentration in the depleted component and decreased in the enriched component. And so what you find here is that, and so 0 would be natural, right? Because 0 is right here. These are workers at this plant, and you will find that most of them, the bulk of the little dots here, are within the sort of, they got natural uranium and they don't have any uranium-236 in them. But you find workers that have increased concentrations of 236, but depleted uranium, that's what this is, because it's lower than 0.07. Plus, here's a worker that has a lot of extra uranium-236 and a lot of extra uranium-235, right? And this, we know that this was a plant that was working with enriched uranium and depleted uranium. And so, here's a person that was exposed to enriched uranium, so extra 235 and extra 236. So this is the plant. This is a little bit of data. This is from a paper by a guy named Parrish, this person in England that does a lot of studies of uranium in the environment. So this is a photograph of the plant. It's in Albany, New York, in upstate New York. You can see, the highway, and this is like residences and so forth. And these are concentrations in the soil. And so, basically these dots are where it was measured, and the size of the dot is supposed to reflect the concentration. So the big dots are greater than 300 ppm, the little dots are less than 40, and everything in between. And this is like a heat map interpolated between these points. And so this is the processing plant. And you can see that, at the plant, this is a half a kilometer, right? So this thing here is greater than a half a kilometer, less than a kilometer. And the size of the heat map in this particular study was limited by where they were able to take soil. So they've subsequently gone back and found that this plume actually extends much farther than this is indicated here, but they basically only sampled, in and around the plant and not into the homes and so forth. And you can see pretty high concentrations. All these concentrations are crazy high. Like I say, naturally in rocks, even in places where the rocks have very, very high concentrations, this would be 5, right? So even 40, even the lowest thing on this plot is nearly 10 times natural. And obviously these highest ones are much, much higher. This is a follow-on paper where they extended the study a little bit farther. It's the same group, but a different person is the first author. And you can pull these papers down if you're interested to look at them in more detail. But this is basically the sort of, again, the heat map, and they still haven't been able to continue the study to the south. So that's why it says poorly constrained. But this is the plant, and these are the concentrations expressed as now in isotope ratio. So instead of the concentrations, is a ratio of the uranium that is depicted, the 235, 238, and pretty much all of these abundances. So this is times 10 to the minus 3, right? So if we, the number is 0.007, which is 7 times 10 to the minus 3. So these are getting close to natural up here in these yellows. They're still a little bit perturbed, but all these other colors have values of 235, 238 that are lower than natural, which means they have depleted uranium in them. And you can see that, the depleted uranium extends pretty far away from the source. This is basically also just a measurement of the typical wind directions, because most of the uranium was introduced here in aerosol form. And this is a plot of sort of a whole bunch of soil particles looking at the 235-238 ratio and the 236-238 ratio, and kind of identifying in all those soil samples. There's sort of two populations. There's the natural stuff that's over here. There's a lot of contaminated stuff, and samples sit along a mixing diagram, whether we're looking at 236, 235, where the inset is 234, 238 versus 238, 235, 238. So we see mixing in both cases, and we see end members of a lot of depleted uranium introduced into the environment. Not tons of evidence of enriched uranium. It's out there. We know the plant was using it and so forth, but the bulk of the samples, the bulk of the distribution was depleted. And remember, we talked a little bit last time about looking at the peak of lead-210 and the peak of cesium-137 in soils and trying to deduce time from that and the period of time of nuclear test treaty, etc. The above-ground test cessation, which was in 1964. So this is a soil column around the plant, and it shows you the concentration. These are a couple of different ones. Isotope ratio and concentration of uranium. And you can see that it's low in the soil horizons that represent before 1963, comes up and reaches high concentration and stays high, very low but high until about 1984, which is when the plant was closed. And then the surface soils are starting to show a recovery. There's a high concentration of uranium with an isotopic composition that's characteristic of depleted uranium in the soils. And we can tell time in the soils by looking at the nuclear fallout signal. And this is just sort of what the uranium looks like. It's in a bunch of different particles. Some of them are like spherules. Some of them are more complicated particles. They're all relatively small. These are scanning electron microscope SEM backscatter images where you look at the backscattered electrons coming off of them, and based on their energy, you can tell what the composition is. And these biggest peaks are uranium. None of them are pure uranium, but these are just particles pulled out of the soil. And so this is getting into the environment. Okay, so now let's switch gears and talk about uranium in Hawaii. And the reason, I'm talking about this is because it was discovered in the late 2000s, 2007 or 8, or at least it became public knowledge that the military had used depleted uranium. Okay, and this was not too far after the second Gulf War, which is when people really started to wonder if depleted uranium was one of the causes of the so-called Gulf War syndrome. The short answer is it probably wasn't, but there was a lot of knowledge around the world about the U.S. military and other militaries' use of depleted uranium weapons. They were clearing an area at Schofield to support a Stryker brigade, which meant clearing out a whole area of the bombing range, the firing range, and some other things to support this brigade, which was going to be used as a fast action force based here and could be deployed to other places. And in the clearing of that range, they found a bunch of depleted uranium munitions that they weren't being used by that group. They had been used there before. It was only someone who had been associated with the Schofield barracks for something like 30 years that remembered what this stuff was and was able to identify, oh yeah, that's depleted uranium. I'll tell you that story in a second, but the kind of questions that you want to ask and you want to be able to answer about uranium contamination is, well, how much uranium do we naturally have here? Is uranium mobile? How does it associate with particulates and organic matter and stuff? Is this a concern for people, like the depleted uranium locally or across the state? How much radioactivity is there? So there's a lot of questions. People were concerned. So this is the weapon that was used here, super top secret weapon. It's called the Davy Crockett, of all sort of crazy names. It's what's called a recoilless rifle. This was invented in the peak of the Cold War, super top secret. It was used here in Hawaii as part of what's called a battlefield tactical nuke. So it's a spring-loaded weapon where basically it's got a radioactive warhead, a plutonium warhead on it that can't fire very far. It's like a kilometer. This is sort of like, oh, the Russians are coming over the hill. Bang, I'm going to take them out, and I'm going to take, it's like a suicide weapon. The weapon itself, as far as we know, was not fired here. However, it's got this thing, you can see it down here, called the spotting round. These were projectiles made primarily out of depleted uranium with what's called a white phosphor tip that, it sends out a smoke plume and an explosion when it hits. That you would do the spotting, which is basically, dialing in the degrees and the angle so that the projectile, if you were to fire it, you know where it's going to go. So they fired those things a lot here, right? There were thousands of those things sent here. This is all pre-computer, really bad paper record era, late 50s, early 60s. We think there were thousands of things sent here. We can account for about a few hundred of them. We don't know where most of them are, where they were used, what happened to them. It's very possible that they were dumped offshore with a ton of other munitions. I do a lot of submarine work in the nearshore environment here, and there are places that are just full of bullets and mines and bombs and everything. But in any event, we don't really know. But we do know that a lot of these things were used, and we know where they were used, and it took a little bit of time to figure it out. The important thing, that the main key thing about this weapon is that this is like a thing that's firing at a ballistic trajectory and not at what we would call kinetic velocities. So these kinetic energy penetrators, the real high energy things that penetrate, that make the dust and all that stuff that we were just talking about, those aren't these. When these things are fired, they shoot off into the environment, they make this little smoke plume, and they disaggregate a little bit, but they're not making the aerosols. And when we go into the field and find these things, we can find tail fin assemblies that are this big. I'm not saying they're good, but they certainly don't make the cloud of dust that people were concerned about for depleted uranium. And so the short answer is that the hazards from this are relatively small beyond right there at the point of use, compared to the kind of modern kinetic energy weapons. And besides being called the Davy Crockett, it's called the M101. And these are things from the Honolulu, back when it was called the Advertiser, before it was called the Star. So if we look naturally here, these are the kind of places that we have uranium and the concentrations that we have. And you'll see that they're all around 2 to 3 ppm or less. So that's considered relatively low uranium concentration. Many of our rocks have a lot lower than that, less than a ppm. Like if you go to Kilauea volcano, you'll find that the rocks there are erupting with about half a ppm. Concentrations in our waters are typically pretty low as well. Seawater has got about 3 ppm globally, which is the reason why corals have about 3 ppm. But it's pretty easy to spot contamination here because we start with really low concentrations, right? And if you think about the sort of typical radioactivity in the natural Hawaiian soil, you'll see how much of it comes from uranium, how much of it comes from thorium, and how much of it comes from potassium. The bulk of the radioactivity that we are exposed to here, and in most places, uncontaminated places in the world, comes from the potassium, not the thorium and uranium. Our rocks are particularly low in thorium and uranium, so our slice of the pie is a little bit lower, but still, it's not a gigantic number. So now if we think about, we've introduced one of these metal rounds into the environment. They're not making the aerosols, so we don't really have to worry about that. But we got these chunks of metal that are sitting out there in the field. What happens to them? So they disaggregate as they oxidize, and there's wind, there's rain. So we can basically have to test for 3 things. One is mobilization of uranium-rich particles, one is runoff, and one is what happens when stuff goes into the ground. The short answer is that these are dense particles that are probably not mobilized very well by the wind because they're big and they're oxidized. When uranium gets into the ground, it binds, if it dissolves, it's going to bind up the iron-rich particles in the low pH environment in our soils, so we get very little mobilization and runoff. And these are things that we have tested and proved with analyses of each one of these environments. I would say not completely. I mean, this is me being a little bit political here, but when you work with a government agency like the Army, they sort of do the minimum measurement required. It's not like scientific research where we do the thing that we want to understand what's happening and we'll like study stuff in gory detail, maybe too much detail. Here they basically just do like the minimum. And the minimum analysis basically shows, yep, there's uranium contamination out there, but it's not migrating. And you can punch a lot of holes in it, but that wasn't my job. My job was to basically help explain. I'll just show you a couple more slides. We're probably not going to get through the whole thing because we're running at a time that you can read the rest of the presentation. But so there are various firing ranges in Hawaii where we know the stuff was used. Schofield Barracks is the biggest one. The firing range of the barracks is nestled up here in the Waianae Mountains. We know it was used at Makua Valley. Makua Valley is this complicated legacy. There hasn't been much military activity there since sort of mid 2000s, when the Hawaiian activists basically were able to convince the military to stop using it. But what they used to do is sit off here like with Navy ships and fire stuff into the valley. And the interesting thing about, there were also Army applications there too. It's now become a very vegetated valley, which makes it very difficult when there's unexploded ordnance on the bottom to find out where the contamination is or isn't. And they're like religious sites that they will take people in escorted and they can go there. But we have not been able to study this place very well because it's so vegetated. This stuff's been studied in gory detail. And, they've admitted to using depleted uranium. This is the results of uranium concentration shown in Z-scores, which are basically numbers of standard deviations above the mean in the soil. Each of these lines represent passes. There are devices called field blurs, which are basically something that you tow behind a vehicle, and it's got radiation detectors on it and detect radioactivity. This is really difficult, hard work to do because it's an active firing range. They still use it today. There's all sorts of unexploded ordnance. And so the people who go out and make these measurements, this is not me, have to be very trained. It's slow and tedious work. And so you can see that there are places with, lots of uranium and not as much uranium, but there's uranium in a lot of different places. And these are this is the Waianaes over here, and this is the natural drainages on the firing range. There was a secondary area that I wasn't actually even able to visit, but it's a little bit to the north. I think they do like more secret-y stuff there. but you can see that the uranium is more localized. It's in a few places, but it's not spread out. Whereas compared to this was uranium, like I said, it was used in the 60s in a firing range that has been actively in use and is still in use. So you can imagine you're just like firing a bunch of stuff and watching it explode, and you're distributing your uranium out. So this is spread out a lot more than this stuff was. So this is kind of what the uranium looks like. We can find the yellow cake. These are the tail fin assemblies that, they don't break apart. More or less they break apart. But this is how we know we probably didn't get the small fragments. And, soil samples are analyzed and so forth, but mostly it's big fragments. So, this is basically sort of a summary of, what happened in this environment, the amount of excess radioactivity in the soil, and it tends to be localized to the point of use in a place where civilians are certainly not allowed to go, and even most military personnel are not allowed to go. But the Army did what's called a BHHRA, a Baseline Human Health Risk Assessment. It's kind of like, we've talked about these kinds of assessments before. You think about all the different ways in which people might interact with the firing range at Schofield Barracks, people who live on the barracks, people who work at the firing range, people who are at the firing range occasionally for training. Each one has a different amount of exposure, and there's basically an EPA assigned threshold for uranium contamination. It's considered safe or not, which is converted into a hazard index. And even in the worst case scenarios for the types of uses, people that were working at the firing range, because you don't walk out on the firing range where the contamination is, and it doesn't seem to be spreading into the environment, had a risk of excess uranium exposure that's like 1/10 of the typical uranium hazard for natural uranium. And so, basically maybe an extra 2 people in 100,000 might have some kind of exposure risk. It's considered a reasonable risk. I'm not excusing the military, but the radiological risks, especially from this uranium, are pretty small, right? Because it's less radioactive than natural. I'll just go show you a couple more slides. If you have to leave, I understand, but I'll just go through this so that for the video. So the other place that we know it was used is Pahakaloa Training Center on the big in between Mauna Loa and Mauna Kea. I don't know, things are a little bit different now. They've redone the saddle road, but in the olden days, if you drove the saddle road, you go right through this thing. And the thing about PTA that's kind of weird, in my opinion, is that it's like a bombing range. They will send planes here, like without radar or whatever, from the Philippines or bases in Japan, and they'll drop bombs here. And like it's like, I don't know, doing stuff without instrumentation. That's only one of the things that they do, but they actively drop stuff here. And this is also a place where depleted uranium had been used. And so there's a lot of concern, especially, I would say, within the state, the people that were most concerned when the information about depleted uranium came out were living in here in Kailua Kona. They're like, oh, well, everyone's buying Geiger counters, and they're worried about extra uranium, and is there a cancer cluster here? And it's related to this. And the short answer is no way. This is way too far away. There's no particulate. There's no uranium transport and groundwater over these distances. As far as we can tell, the uranium that was used there are just like sitting on the ground like this, right? That doesn't mean to say that it isn't theoretically possible, but if you go out and buy yourself a Geiger counter like on eBay or whatever, you don't have any calibration, they're super sensitive to water, the head absorbs water, it can tick, for all sorts of electrical reasons other than being exposed to radioactivity. And so, I had to do this demonstration for people. It's like, okay, here's what some real radioactivity sounds like when you hold it in front of a Geiger counter, and you could peg it for them, and they're like, oh, okay. Here are a couple tips, is not it. But as I say, this is a place where we do find some, again, I wasn't involved. What they did is they basically fly helicopters over the range with radioactive detectors on them. They look for hot spots. And then when they find something, they hover and they send down a soldier who picks up some stuff and brings it back up to the helicopter. What's interesting about this is so different than Schofield. Schofield is like a really wet, tropical environment with aged soils. This is a lot of bare rock. It's very arid. It's almost alpine. It's just like 7,000 feet. And so the uranium behaves differently. We don't find as much of the yellow cake. This has still got its paint on it, the tail fin paint. It's just barely oxidized. And this is just, an idea of what it looks like. It's mostly surface lava flows. There's a little bit of soil in some places up here when you get closer to Mauna Kea, which is an older volcano. But as far as we can tell, the uranium that was released from this environment, like I said, these are bare rock. This is an eruption in 1935, et cetera, et cetera. The uranium is just sitting on the surface and is not getting into water. Now, the third place that's more questionable is Makua Valley. This is what it looks like today. There's unexploded ordnance all through here. It is not safe to walk through because of all the trees and the foliage, because they ironically stopped doing the firing there. It's hard to know exactly how much is there. So all we were able to do at this site is look at water that's running off of it. Uranium, there isn't much uranium in the water that runs off of sites anyway. And as far as we can tell, there's no uranium migrating off the site. Now, you say that to the Army, and they say, see, there's no uranium in the site. It's like, no, that's not what I said. I said there's no uranium migrating off the site. We don't know how much uranium is in the vegetation. We don't know how much is in the soil. We don't know how much people are being exposed to, Native Hawaiian practitioners that are going in there to these specified places. But they're probably not getting much exposure because they're going to the places that have been cleared, right? So we don't have the answer to that, but this is just sort of the summary. These were kind of the public concerns, and I would say there was a lot of media reports. It was in all the newspapers and it was on the news all the time. The state was very worried. They wanted to set up this monitoring program. They were worried about uranium migration off these sites. And I think that was not justified. The type of uranium that was used here and the conditions in our soils and so forth mean that we don't have much risk outside of right there at the sites. This is a test burn. They do these not test burn, but I can't remember what they call them, but they basically light fires around the firing range to kill off all the vegetation to sort of make it clearer. And so we put out some air filters at this time and filtered the smoke to see if there was any uranium in there, and there wasn't. The thing I will say, and again, this is like kind of one of these complaints about the military, is they could only get air filters that filter at 2 microns. And I think that the particles would probably be smaller than that if it was there. I don't think it's there in other places where they've tested for it. This is too low energy of a fire to circulate a lot of uranium. But it's sort of like, yep, they did the test. They could check it off the box, but they didn't do it the way a scientist would do it. But nevertheless, I don't think we have the very fine particles. So I'm pretty sure that was, I had another thing. This was another slide I made for public concerns about monitoring. This is basically just saying, don't go on eBay and buy yourself a Geiger counter and expect to get meaningful results. You have to be trained how to use these things. You have to keep them in certain conditions. They need to be calibrated. They need to be cleaned. All these connections are sources of electronic noise that can make these things tick. And you have to hear a lot of ticks before there's any radioactivity. And I mean, I definitely feel for people. There were people that were very concerned in certain parts of the Big Island that they were receiving radioactive doses. And, people who have a health concern about something in the environment, you have to treat them kind of with respect and understanding. But, in essence, the amount of radioactivity that they could possibly be exposed to from that uranium use is way less than their typical dietary intake that they're going to get from potassium in the bananas that they eat. It's orders of magnitude. And there's probably nothing detectable, right? And in any of these environments, just unless the military has used it in other places that they haven't told us about. And one of my big questions is Kaho'olawe, which I've been able to go to. There's a lot of still uncleared areas. I'm suspicious that there is uranium there, although when I talk to munitions experts out there, they're like, oh, no, we've never found any of that stuff. I don't know. So you don't know. But as I say, what we do know is that they sent thousands of these things here, and we can only account for 100 of them. So they're out there somewhere. Maybe they're all in the ocean. Maybe they were disposed of. Because it was a super top secret program when it was happening, right? And it's now only, coming out like a half a century later through Freedom of Information Act stuff. This is like the pre-computer days. We really don't know the details. So I'll stop there. And thank you. Sorry I went long. Do you have questions?